First of all, I want to say thank you for coming. I'm very happy to be in New York and very happy that people actually care about what I do to come and have lunch with us. I'm from Cornell University. I'm an associate professor. I just got recently tenure. And everything I'm going to talk today is available in our website. You can go to nanotextileshuman.cornell.edu or simply Google nanotextiles and Cornell, and we usually come first. So I'm very happy, but before, so I'm going to talk about the intersection between fashion and nanotechnology. So that sounds a little bit strange, but hopefully by the end of the talk, I will be able to convince you that basic science can have an interface with fashion and many other fields. So I want to say thank you to the people that pay my bills. These are the organizations that support my research for the last 6 years: the Department of Homeland Security, the Defense Threat Reduction Agency, the National Science Foundation, the Department of Commerce, the National Textile Center, the USDA, the Centers for Disease Control, the Red Cross, NIOSH, 3M. But in addition to being a scientist, I'm also a big fan of NASCAR. And that sounds a little bit strange, yeah? So, but I like NASCAR very much, and I follow their strategy. So what the NASCAR people do is in their car, they paint the logo of the sponsor. So what I did here is the amount of pixels of each logo corresponds proportional to the amount of money they give me. So the bigger the logo, the more money I get. But in total, there are about $6 million there. So if you want to have your name there too, we can talk after. I'll be happy to put your name. There were some of these organizations that complained that their logo was too small. And I told them there was a solution for that issue. This is the website. Probably many of you visited. We have basic science. We do basic science. But we also do a lot of interactions with community, with kids, with senior citizens. We also do interactions with teachers. Try to get our kids interested in science and discovering as an incredible, powerful tool to be better in life. I think that there's an incredible power in discovering new things, and that's what we do. And we have some of the media issues that we have here. So everything started when about 2007, I was asked to talk about the connections between fashion and chemistry. So I wrote an editorial, and they chose the title called Nanotechnology Can Be Fashionable. And these are two dissimilar things. So I will not present the video, but the video is available in the website. Maybe I'll do it, but you guys can eat, so it's only 2 minutes. So this is a video we did about 2 years ago with Reuters.
This is a very special pink dress. It works perfectly for a night out in the town, but it can also charge your iPod or cell phone if you left the house in a hurry. The pretty pink dress doesn't come from a French fashion house, but from scientists at a Cornell University laboratory. Professor Juan Hinestroza and his team are working on creating what they call smart cotton.
This is cotton that is treated with nanoparticles, with nanometals, with nanopolymers, with nano-oxides. And these different combinations of groups provide them with unique functionality.
One of these functions allows the cotton to conduct electricity. The team show how 2 strands of cotton hooked up to a power source can act like cables to illuminate a small light bulb. He says our clothing will soon be designed to do a lot more than just keep us warm and look nice.
Our goal is to have an interactive surface that will be able to sense and to react. It will be able to sense temperature or pH of composition of gases, and then react accordingly.
And Hinestroza says that in a not too distant future, our clothing will be able to do things like monitor our health, adjust to changes in temperature, better protect us from harmful UV rays, and have the ability to connect wirelessly to the internet.
I am wearing this blue sweater, and then it's St. Patrick's Day. And then I forgot to have my green sweater. I can just pass an electric current, move some of the nanoparticles in my sweater, and they become green. And I can create color with single nanoparticles.
Hinestroza says our knowledge of how to manipulate particles on a nanoscale is increasing every day. And as that knowledge base grows, so will our ability to create smarter clothing. A pretty pink dress is just the beginning. Ben Gruber reported.
So this is just an example of what I say. I was going to show you that actually that's a reality now. And that's what we do. I like this particular slide because it's not from a chemistry group, but it's actually a business prediction analysis. So it shows that since the 1800s, every 50 years, you have an industrial revolution. And that revolution is based on knowledge. A change in technology that changes the way you think. So, and you make tons of money. You create wealth based on knowledge. So in the 1800s, textiles was the major industry. Then there came the railroad, the automobile, the computers. And now we believe that nanotech is another industrial revolution. And you can see that these industries grow really, really fast, and they become very well established. So the textile industry is very well established now, and the nanotechnology industry is starting. So what I do is basically I merge 200 years, industrial revolutions that are 200 years apart. And what I like to do is to combine something very old and traditional, like textiles, with something new and revolutionary, like nanotechnology. And hopefully by the end of the talk, I will convince you that nanotechnology in textiles is not an oxymoron. So hopefully that's the goal. So everything started with protective clothing. I worked with this issue on my thesis. Basically, if you want to be protected against everything, you just create a bubble around you. So you prevent air or liquids or gases or vapors to go through. But at the same time, you cannot breathe. So you are protected, but you are very uncomfortable. And most likely, you can only be in that level of protection for a few minutes. What the military has done is creating these materials that have a layer of carbon that allows some of the air and liquids to go through. You trap some of the bad chemicals and allow you to breathe. But these layers are very, very heavy. What we decided to do is to eliminate that carbon and create individual layers of polyelectrolytes. And these layers are very, very small. Now, you imagine that when you are in the winter time, you put 2 or 3 pieces of clothing, you become warmer, but you suffer immobility. Yeah? You cannot move if you have 3 shirts on you. So imagine you want to protect against 10 different threats, 10 different gases. You have 10 different shirts. It becomes very difficult to move. So what about if we make these layers very, very thin? So thin that it can be only 1 molecule in thickness. And that was the proposition that we did. We wanted to ensemble layer by layer, single molecule at a time. And it's basically the same way you do a sandwich. You have a substrate, and then you put different layers of cheese or ham, and you build your sandwich, your structure, one by one. So this is one of the few chemistry slides, so I have to show it because that's my society. But basically, this molecule here, this weird molecule here is cellulose. It's cotton. So I wanted to work with cotton, and I make cotton positive. And then when I make cotton positive, I could deposit negative layers onto the cotton, and then a positive layer onto the negative, then a positive, negative, positive to create a sandwich. So what we did is we created these structures that have 40, 50 layers, and each layer has a different polymer. And each single layer, if you go here, this one has 20 layers, and it's about 400 nanometers. So each layer is only 20 nanometers. So you may wonder what a nanometer is. Many of you know. But if you look at the diameter of your hair, it's about 50,000 nanometers. So I'm working with things that are only 20 nanometers. It's about 2,500 times smaller. So imagine your hair, and I cut it 2,500 times. That's the type of dimensions I do work on. And you can see them here. This is about 20 nanometers, each single layer. And each one of these single layers can prevent a gas from moving through the clothing. So you can have, in this case, mustard gas and nerve gas. This was done for the military. You can control how they move, what speed they move. But you can also control how your humidity moves, sweat, how the water gets out or gets in. You can control that movement of liquids and gases through your textiles. In some sports, it's very important to get the humidity out very fast. In some, you need to have a layer of water being an insulator. So we can control how this water moves away or comes in. In days like today, we have a horrible humidity in New York. So we want to have everything that gets condensated in your skin, you want to get it out, yeah? So we can manipulate that, how fast that can happen, by single 20 nanometer layers. So at that moment, we decided that these 20 nanometers were too big for me. 20 nanometers was too big, so I wanted to do it smaller. So instead of depositing molecules, I wanted to deposit atoms, much, much smaller, 50 angstroms. So 1 angstrom is about 1/10 of a nanometer. So it's 10 times smaller than the previous small. And we did this. This is the similar process that you do for making integrated circuits in computers. So we have these layers of metals depositing on that, and we can coat the material in a very conformal way. So this is how a cotton fiber looks. If you look into the microscope, and then these dark spots here are actually atomic layer deposition signals here. Now, why do you want to do that? Well, we wanted to do that because we wanted to grow these layers that actually block radiation, UV radiation, so you don't get sunburn. But at the same time, it doesn't affect the color of your dress or your shirt. It doesn't affect the comfort, but prevents you from being exposed to these rays. And these layers are so small, you cannot see them, you cannot feel them. There is no difference for the person that uses them, but they are actually there protecting you. We also did a study, and we were able to improve the thermal insulation values of these layers. So imagine that you, in the winter, in February in New York City or in Ithaca, well, most of the time in Ithaca, you can go outside with the single cotton T-shirt with one single layer of this aluminum oxide. So it provides the same thermal insulation as having your fancy heavy jacket, but it's a T-shirt. So that's one of the things that we do. We decided to move later to do single nanoparticles. So these nanoparticles, the same principle, we coat them with negative groups, and they assemble onto the surface of the cotton. And they assemble one by one. And then we have examples here of the silver deposited on cotton. This is the view from outside. If you do the cross-section of the cotton fiber, you can see the cotton fiber here, the layers of the cotton, because cotton is actually a growing entity, so it grows layer by layer. Those of you who have experience in farms, you know how plants grow. They grow slowly, and it's one layer after the other. And here are my nanoparticles outside. We also did it for gold. Oh, this is the verification that actually that's silver. This is for gold. And this is a picture that is amazing for me because it shows that cotton is a living fiber. You can see the channels providing the nutrients to the cotton. You can see the layers growing of growth. And you can see the particles one by one coating a single fiber of cotton. And we also did that for platinum. So we did silver, gold, and platinum. And so that was one way to do it, but we have 2 steps. My student decided, I have a second student that liked the project. She wanted to do it in one single step. So she said, well, cotton has these little porosities inside. Why don't we do a chemical reaction inside the cotton? And actually, it worked pretty well. So she put the reactants inside the cotton, do the reaction, and then you created very beautiful coatings on the cotton fiber. So imagine your T-shirt is actually a chemical reactor. So you have a T-shirt, you can make reactions there and make materials that are very, very small. Now we are working on that, creating these unique particles. And we were able to put silver, put gold, but we couldn't put silver using this method. And this method was very complicated because we used positive cotton and we needed positive ions. And silver only has positive ions. So we cannot put positive on positive until I have a postdoc that came to my group. And I told her, OK, this is your project. You have to put these particles here. That's what I want. And then she said, well, it's not possible to bring the particles to the substrate because they have the same polarity. And then one day she shows up in my laboratory and says, you know, professor, if Mohammed cannot go to the mountain, I'm going to bring the mountain to Mohammed. And I didn't understand what she was saying until the next day when she was this very clever approach. She made the cotton negative. And then when the cotton was negative, she was able to bring the particles and we're able to attach that. A completely different change of the paradigm that we have. And more important, we were able to put the particles so close to each other. So look at here. This is 200 nanometers. So this is about 250 times smaller than the diameter of your hair. And these particles don't agglomerate. They are one next to the other. Now, this is smaller than the wavelength of light, so we can play with light. So if the light comes here, the bouncing light will have a different frequency. And that is represented by changing color. So we have these wonderful things, but we didn't know what to do with them. We can put the particles so close to each other, but we want to find applications. I have another student that likes to kill things. So I say, well, be my guest. So decided to kill bacteria, kill E. coli and Staphylococcus aureus. So those are very, very tough bacteria. One is very present in food, one is in hospitals. And she was able to achieve 10 to the 7. That means that out of 1 million bacteria in contact with this material, 1 or a fraction of 1 survive. So we cannot count a fraction of 1, so we have to say 1. But this is the bacteria. This is after we expose it to the material. So it's very good killing bacteria. And also, I know there's a lot of graphs here, but this is basically, we did it to test that we can detect explosives, and we can detect drugs, and very dangerous compounds at very small concentrations. So almost 10 nanomolar, which is almost single molecule. So if you have been exposed to an explosive compound or a drug in the last 2 months, we can actually detect that from your shirt, from what happened in the past, by simply controlling the spacing and the signal coming from the nanoparticles. And more importantly, we can control light. So we can control light, and then we can create color. But we create color that is physical, it's not chemical color. So most of us have clothing that is colored with pigments or dyes, yeah? So after you're exposed to the sun or is washed, the color fades. Physical color doesn't fade because actually it doesn't have any chemical ingredient in that. It's only the interaction of light. So imagine a T-shirt that will always look new, always look sharp, or a car that always look brand new. And we can make gold to look, silver to look like gold. It's a silver. Gold to look red or purple, or platinum to look like gold. And we can change the colors. Now, I have a student, I happen to be in a department in which we have half scientists and half designers. So I have a fashion designer in my student that like these colors, and then she told me, I want to make a dress from your fabrics. But all we do is very small samples. But I'm a faculty member, and I never discourage a student with a crazy idea. So because one upon a time, I was that crazy student. So she said, well, let's do the chemistry to see what happens. So she wanted to make a dress using colors only produced by nanoparticles. And here she is. So this is Olivia Ong. The person on the right is Andrea. The person on the left is Nicole. They are modeling the dresses. All the colors in these dresses are coming from nanoparticles, no pigments. So the blue one is gold. The yellow one is silver. The brown is palladium. And all that was made by simple controlling of how the nanoparticles space and the size of the particles. And we can see them closer here. So all this is gold, these blue ones. This is silver. Now, by the way, my mother doesn't believe me that gold can be blue or red. but because she says it has to be gold. But at the nanoscale, it can be any color. It's the same material, but you can control the sizes, and you can make any color from that. And one of the things that happened after that thing was that we have a lot of people in my lab, a lot of journalists trying to cover the news on that. And it was very interesting for us from the teaching perspectives, because designers think very differently than scientists. Scientists, what we do is we take a problem and divide it into small pieces. And we solve the small pieces, and then we solve the problem. Designers think completely opposite. They solve the entire problem first, and then they try to look at the individual solutions. So this interaction of ways of thinking between a scientist and a designer were incredibly rich for us as scientists, as for them as designers. So she's doing very well. She's making tons of money. A few months ago, we met, and then I said, well, when you will be rich and famous, I said to Olivia, remember who made you famous. Yeah? And then she said, you know, Professor, I think I was the one who made you famous. But she was absolutely right on that. Now, as a scientist, I like to be on popular science in the Daily Telegraph, but she only wanted to be in one single journal, which is this. How many of you guys know this? Yeah? Yeah. Okay. So if you are there, you are set for life. That's what you wanted to be in the Women's Wear Daily. For those of you who are not familiar with that, that's the top notch. For us, the second thing that we did is we have visitors from the military, but they didn't want to create color. They were interested in making color invisible, disappear, make color disappear instead of being created. And we use the same principle. We put particles on the surface of the material. We manipulate how the radiation goes into the material, and we make the materials outside the visible range. So these materials are actually invisible to near infrared, which is the same radiation that they use for the night vision devices. So it's the same principle. I can make color, or I can make color disappear by using these little particles. The other thing is I put the particles so close to each other that I can create these little cushions of air between particles that prevent any liquid, water or oil-based, to actually touch the surface of the material. So I can expel water, oil at the same time, and allow the air to go through so it feels fresh. So what do you do with something that can repel water and oil at the same time, kill bacteria, and allow the person to be fresh? One application that we never imagined was in the fast food industry. People in the fast food industry are exposed to water and oil all the time. They have to be fresh, and they cannot have to prevent bacteria prevention also for food packaging. When you ship fruits from overseas in Asia or Latin America to Europe or the US, some of these fruits emit some gases that you want to protect from damaging the fruit. So this was actually a collaboration with a company and a professor in Italy. But what that really bothers me is the particles were so close to each other, but I couldn't pass an electron. So I wanted to have an electron jumping between particles, but my fiber didn't wet, didn't become, I cannot do water chemistry, I cannot do oil chemistry. So I have these brilliant students from Italy that said, well, if water or oil doesn't wet the fiber, why don't we use a gas? And that was a very clever idea. So she used a gas and was able to make a chemical reaction that created a bridge between the particles. And this bridge is very small, only 4 or 5 nanometers, but allow me to transfer an electron from one point to the other. So I want you to take a look at this picture here. This is a light, and it's called an LED, and this is the power source. And this light is connected to the power source not by a wire or by solder, but a single thread of cotton. In fact, I only have a knot. And in this case, I only have a wrap of cotton around the LED. So I'm able to transfer electricity the same way I can do it with a wire. But it's flexible, it feels like cotton, it drapes like cotton, because it's cotton. So what do you do with that? Then I have this wonderful student. You can see here, even a single node conducted electricity. So I have a student, who's also a designer, and she wanted to have her iPhone always charged, and she has this issue with the battery. So what she decided to do is to put solar cells on the dress, and then connected the solar cells to the charger of the iPhone by using a thread. But the thread was coated with our nanoparticles. So at the same time she was making the dress, the thread was able to conduct the electricity from here to the charger. So it was a combination of these two approaches of the designer and the scientist. And then you have your dress that charges your iPhone. And that's the one you actually saw on the news. So that's my wonderful student, Abby Lippen. And this is the dress right here. So the next thing we did is we work with things that are cheaper. I said, well, these particles are very expensive. Let's work with carbon black. This is the same pigment that you use in tires. So I am almost sure that all of you have black clothing in your closets. I can guarantee you that 99%, if you buy a black shirt and a black pants, they don't match. Is that right? OK. Why they don't match? Because this is a chemical color. So they have a different hue. But what about if we can make a physical black? A black made from these little particles that have atomic uniformity. So we'll always be black. And this is very important for the industry of tuxedos, when you really need to have the black under any lighting conditions. So you have these particles capturing the lights and making the black black. So we did that. We can put the particles with atomic precision on each individual fiber. And the latest things we are doing is we are working with these metal organic frameworks that are able to capture gases. So these are beautiful molecules that were discovered by Professor Yagi at UCLA. And I'm very fortunate to work with him. These molecules you can engineer to capture a specific gas, and then grow them into cotton. And this is one student that, this is my samples. My student saw this color and said, well, I want to make a dress of that. She likes sports, so she made a jacket that has these covers that can capture some gases. And here is the jacket, so in case you guys want to take a picture later. So all the blue color here is produced by copper. But all this, if you touch it, it will feel like cotton because it's cotton. I only modified a few nanometers of the surface, and I'm able to capture gases in a selective manner. So imagine all the applications. You are outside. You are exposed to all this exhaust from the cars. You can filter them. Police, fire responders, or military that are exposed to dangerous chemicals in an incident, they can be protected against all these chemical warfare agents or even industrial toxic chemicals, and at the same time be comfortable. So we can detect what gas is being present and capture before it actually causes any damage. So this is my wonderful student, Jennifer Keane. This is my office. And that's Alan. We couldn't convince Ellie to come, so we have the mannequin here. So hopefully by this time I was able to convince you that we can make nanotechnology fashionable, or maybe we can make fashion amenable to nanotechnology the other way around. But the combination of science and design can offer so many opportunities. And we in Cornell, we are very fortunate to have a department that has, it's one of the few in the nation that has scientists working with designers. And this a few minutes ago, I was talking about the student that went to work for Nike. So he designs shoes, but he has a very strong background in science. And he's very successful in designing because he has his science background. And that's the story of the students at Cornell. We have this all-around foundation that allows them to excel in whatever they do, but they have a very strong foundation. So everything I do is available here. And I will be more than happy to answer any questions that you guys may have. Thank you. Yes?
When you were talking before about the invisible technology, is the idea with that they can blend in with anywhere, or if they're wearing it, it's like literally an invisibility cloak that people can't see them through?
Yeah, well, there is no such thing as invisible, but what we want to do is we were able to manipulate the light. We wanted to manipulate the near-infrared radiation. That's the radiation that you use to look at night. So when you look at night, you cannot see because there are not enough photons from light. So you just shoot a near-infrared beam, and that beam converts the photons, few photons into electrons, then you amplify them, and then you can see an image that is a reflection of reality. So what we do basically is to confuse that reality. So if a person is looking at a soldier in the field, through these lenses, he will see nothing because we manipulate what signal is coming back. So in that sense, it becomes invisible. But we can also do is, for example, take a picture of an environment and then program these nanoparticles to actually reflect the picture so you are part of the background. And then you move to a different environment, then we can do the same in an interactive manner. So you will always be part of the background. That's our goal. Yeah?
Just to follow, in order to actually do that change or to make the clothes change color, how do you do that?
OK. So what we do is the color is created by the size of the particles and how far they are from each other. So I coat the particles with a polymer that is responsive to either light or temperature. So if I increase the temperature, the polymer expands. Then the particles increase their separation a few nanometers, and they create a different color. I can make also the polymer sensitive to the presence of a gas. For example, if I'm allergic to a compound, to ozone or to cat, this polymer is sensitive to the presence of ozone or the presence of other gas, they can contract or expand, change the color, and tell me, OK, this environment, you have something that will damage you, so you better don't get inside, just by controlling this movement between particles. So my goal is, as I told you in the video, is to have clothes that can change colors. I don't have to change. It's the same shirt all the time. It will be black for going to a party. If I want to go to a Cornell event, change my color, it becomes red. Then if somebody throws wine at me, it will not get dirty, it will not stain. And because of the ability to kill the bacteria, it will not smell, so I don't have to wash them. That would be my perfect solution. But we are still far from that. But this is our goal. Yes, ma'am?
Are you sort of wiping out the whole dry cleaning industry and the fashion industry?
I would like to see it like an opportunity to create materials that don't need that type of care. If you are in a soldier environment, for example, you don't have showers in the desert. You have to live 45 days, 30 days without taking a shower. So you need to have, there is underwear that can stand 30 days without washing. And then you kill the bacteria, make you very comfortable. It sounds a little bit gross, but actually it works. And you have, in those situations, you have no choice. So I like to say that this is an opportunity to make a completely new realm of clothing and industries based on technology.
Are any companies, any fashion or apparel manufacturers using this, or?
Not yet. This is what I show you here is the result of our last 4.5 years of work. We have Cornell has the patents, and some companies are licensing those patents, especially for the detection of explosives or drugs, detection if something is a counterfeit. That's a serious issue. In some countries, they think that copyright is the right to copy, and they copy everything. That's the truth. And I've been in those places, and they have full enterprises to copy things. So we can put particles inside those fibers and allow to trace the process. Because most of the counterfeiting happens in the middle of the processing. So the design is sent to the manufacturing unit, and then the manufacturing unit manufactures more items, good for the company and some for the other market. So we can detect when that happened, when these shoes are actually from Nike or from Reebok, or actually Nike with double E or Reebok with double B. Like they put. So this is another industry that we can do. We can do things that are invisible, but you can sense that actually they have a unique signature. Also for uniforms, so you can, like a FedEx guy or a UPS guy can go in any building in the country, yeah? They never ask a person, are you really a FedEx person or a UPS? They can go anywhere. So they have some security measures in some of those clothing that can tell you this is actually a FedEx person, or this is actually a person working at the airport, just didn't steal the jacket or the thing and pretended to be. So there are many other applications in anti-counterfeiting devices, in what we call understanding the actual source of the material. And that's another issue because cotton is produced in the US. It's sent overseas by magic. The cotton grows overseas. When it comes back, there's more cotton than the one you actually sent. So it's mixed with other cottons, other fibers. So there are many opportunities to work with these materials. You have control of the material, and you can embed it into a paper or into a fiber or a textile. Yes, sir?
I've got 3 questions. We'll just start on the counterfeiting aspect. How are they going to be able to identify that those Nikes are counterfeit without taking it into a lab?
Okay, so one of the things that we do is we work with magnetic particles, and we put the particles inside the fibers. They can actually be read by a magnetometer that looks very similar to the guns that you have for price scanning at the supermarket. And they have a very unique signal, and the signal is coming from the position of the particles. Now we're talking about positions that can change 4 or 5 nanometers only. That's very difficult to replicate. You have to know the frequencies and the particles to know exactly that's the actual material. That's very difficult to replicate so far. Eventually, somebody will replicate it. The best anti-counterfeiting measure is probably price. If it's more expensive to copy it than actually buy it, then people will buy it. So you always have to be ahead of the game. But it's a serious issue. It's probably the 2nd largest business in the world, one of the most profitable ones.
Okay, the other 2 deal with the clothing. You're offering it to the military for security purposes. Are you designing it where they can cover their entire body with the material and use it to filter the polluted air through it, or are they still going to have to use a filter system? Okay, so tomorrow I have to go to the Army for facing similar questions. What we do is, I'm a professor, I work at the university. My outcome is knowledge, science, and to educate the next generation of scientists. That's my outcome. In the process, we develop technology and discover things that are of use to many industries like the military that heavily support my work. So they take this basic science and this basic knowledge, and they translate that into a technology, for example, for respirators. We work heavily on respirators, on advanced filtration systems for buildings that can capture those gases. The implementation details, I am not fortunate to know the details, and I'm lucky I don't know them because then I won't be able to tell anybody. But what we do is basically we train scientists, we do the science, and they do the development. The Army has fantastic scientists. Many of them graduate from my group at Cornell, and they do all this development. Obviously, they cannot tell me because now they have secrecy agreements, but our goal is to create the best and the smartest scientists in the world, so the other folks will be behind. Yeah, the 3rd one is you're talking about creating clothes that battles bacteria. Mm-hmm. We have 2 issues with that. One is that some bacteria is good for you. Yeah. So if I'm wearing the clothes on my arm and it's killing bacteria, is it going to kill the good bacteria in addition to the bad? Okay. We could make it selective, and that's a serious issue for us. We want to understand the interactions of these particles with the cells and the skin. So we are partnering with the medical school, because we don't know that part of the equation. We know the chemistry. But in the medical school, they are developing skin models that resemble the behavior of the skin to understand what the allergy issues could be, or toxicity, or you are killing the good bacteria. The answers so far are very positive. There have not been adverse effects, but we don't know the final answer. So we want to make sure that we know all these details before those products are actually implemented. So the best antidote for panic is knowledge. I always say that to my students. So if we don't know, if you get in panic, this may gonna kill me, the best antidote is to learn. Knowledge can overcome those issues. So we partner, we do things ourselves, but we also partner with things that we don't know. So we don't know the medicine, so we have to partner with the medical school. Any more questions? Yes, ma'am.
So you said Cornell has the patents. What is the next, of all these experiments you have told us, that you know it's gonna be out there in the real world next? What is the thing that is coming out?
Okay, I think the antibacterial textiles are coming out, and also the anti-counterfeiting ones are very immediate use. Obviously, the companies that got these patents don't want to know that they are using them, and I cannot tell them, because then people that will copy them will copy them. But those are the two technologies that are moving ahead. We have a company in Ithaca called iFiber. It's a startup company. What they do is take some of these patents or basic knowledge and make it to the middle phase where they scale up the process and the big companies are able to actually prove that they are useful. But the two areas that are forefront are the antibacterial clothing for surgical gowns, for killing bacteria that is resistant to antibiotics, the serious issue now, infection, and the anti-counterfeiting devices and detection of explosives and drugs. So when you go to the airport, you see the guy that scans your clothes, put them in a little device, and sees if you have explosives or not. So we have similar technology, but instead of scanning, you can use a single beam of Raman that will go through your clothing and comes back without you even noticing that you are being scanned.
Who's buying this antibacterial clothing? Is that the Army?
Yeah, the Army have some of those, yeah. Yes, sir.
A question about the copper producing the turquoise color. Is the ionization due to its contact with moisture in the air, or due to its contact with other fibers that are being used in that?
It's with the other ligands that we have. It's basically a copper oxide. It's a copper acetate. So that the oxide of copper creates that color. And the humidity is an issue that we have because these molecules were very unstable, so we have to coat some of these molecules to prevent the humidity from damaging the molecule. But this is a clear example where we can use science with a design perspective. So imagine you have all these things in a place like this. So instead of having a carpet that is nice and shirts, imagine that this carpet can capture smells or can kill bacteria. So I believe that we can get to the point where clothing will be aesthetical value, but also functional. So like I was telling before, when I meet a designer, I can see that the designer looks at clothing like a piece of art, an expression of art. And that's a beautiful thing. But I'm a scientist. I look at that as an incredible amount of surface. It's an incredible surface in the clothing. So what about if I can use my clothing to conduct electricity, to access the internet, to apply medicine, to kill bacteria, and at the same time look cool? So that's the interface that I think has so much value when scientists talk to designers, or buildings, stadiums. Anything that you can imagine has textiles in it, or fibers. Your shoes, your toothbrush, your pillow, your pajama, your clothes.
There's another question. I remember reading that this past, last year's World Cup, correct me if I'm wrong, but I thought all of the uniforms were using recycled materials. So do you have some sort of programming or some sort of area of exploration where you're investigating that, how you can repurpose recycled materials?
No, at this moment, no. We focus on the basic science. Recycling and sustainability is a serious issue, and it's a personal cost for me. And that's what I work with cotton. I like natural materials because the science that I do can be applied to the cotton grown in the US, to the cotton grown in China, in Egypt, in Colombia, in Mexico, in many places of the world. So imagine that you can make this single crop of high value. So instead of just producing T-shirts that you can buy for $5, then how much will you pay for clothing that will protect you against bacteria, will prevent the smells from going, and you don't have to wash? Obviously, the value will increase. So if these farmers can make more money from their crops based on science and knowledge, everybody will benefit from that. Yes?
How close is the technology to the point where you can go into mass production? How long do you think it'll take before it's economically feasible to do something like that? Okay.
Yeah, it's tough questions for me to answer because I don't have a business background. But what I have noticed is that companies see value, they will accelerate the process. Usually this process of taking technology from universities to actual mass use take between 5 to 10 years, depending on how much money you put there in those companies. But I've been in many companies in the US, and I know they are working in very similar approaches. So my guesstimate will be 7 to 10 years to be. And most likely you will not even know it because you don't see it. So that's part of the magic of working at that scale is nothing will change because people don't like to change. We are like the things we are. How old is the suit? I don't know. Any person can tell me? We always have this. Look at the pictures from the 1800s. They have the same style, pants. Things are changing, but slowly. Or the concept of washing. It's a concept that is about thousands years old. Yeah, people always put water and wash, and we keep repeating that. Now we have machines, but why do we do that? Can we do it in a more efficient manner? I'm against washing, but that's my personal bias. Yeah, my girlfriend always complains because I don't wash my clothes, but I think eventually someday we will have clothes that will not need the psychological effect of washing. Any more questions? No? Okay, if not, then I'll have a little bit of lunch because I've been talking, and I want to say thank you so much because there is nothing better for a professor that actually find out that people care about what you do, and that my students are wonderful human beings. They are kids between 23 and 30 years old, coming from 15 different countries in the world. And the only thing they do is to learn, to discover, and to develop new things. And these are the people that are going to make our country different. Innovation is the only driving force of this country. And innovation driven by knowledge is the best way to do that. So you guys are more than welcome to visit our lab in Ithaca. We have new facilities. Just let us know many of the things we have in the website, and I'll be happy to provide supporting materials for the things that we do. Yes, ma'am.
One question. Have you ever done a presentation like this? I hope not as scientific at one of the fashion schools like Pratt Institute or Fashion Institute of Technology. I mean, do they have the faintest idea about what you're doing?
Well, I have not met in those institutions. I have been in contact with some professors because they see the press releases and they see my students, and the students talk to each other. I've been in RISD, Rhode Island School of Design.
Oh, okay.
Yeah. So they have these ideas to make these curtains that could detect the sunlight, and they will immediately contract or collapse, open and close depending on the sun, using nanoparticles. But that's the type of interactions I'm looking for, because they are two dissimilar fields, and if we talk different language, we can get always very good solutions. So this compromise between two different views works really well in science. We don't explore it too well, but we are getting to that point. Any more questions? If not, thank you very much.